Hello and welcome to the next installment of our Saratech Enablement series. My name is Monique Anderson. I'm the marketing coordinator here at Saratech and I'll be your host today. Presenting today we have Edwin Abrahamian, who is an application engineer here at Saratech, and he'll be teaching us about design optimization by means of convergent engineering in Solid Edge and NX. But first, I want to tell you a little bit about the Saratech Enablement series that we've had great success with. We usually run about 30 to 45 minutes and our training is always led by subject matter experts. We cover topics including FEMAP, NX, Solid Edge, Team Center, and much more. So be sure to check out our website for dates and times, which may vary in the coming months due to your feedback. Our goal for the Saratech Enablement series is to help you get the most out of your software, share knowledge amongst each other, and build a community of users that will help empower each other. And as always, this is an open forum. We look forward to participating in the training. If you have questions or comments during the presentation, please type them in the chat box to the right of your screen, and I'll kindly interrupt Edwin and let him know your questions and comments. And with that, pass the baton to Edwin. Thank you, everyone.
Alrighty, hello all. My name is Edwin Abrahamian. I'm an applications engineer here with Saratech. There's a nice little picture of me. So I've been with Saratech for around a year and a half now. Started as an intern straight out of college, graduated with a mechanical engineering degree. I learned a lot of modeling in SolidWorks in college. Then once I started joining Saratech, I got my hands on NX, Solid Edge, FEMAP, NX CAE, amongst other tools, which was great. So today, as Monique stated, we'll be discussing how to optimize your designs easier by means of convergent engineering. So here's a brief overview of what we'll be discussing. So I'll delve into some background on modeling and convergent engineering. I'll do some convergent modeling for you. There's about one demo for that. Then we'll kind of delve into reverse engineering. I'll do a demo on that. And then lastly, just a couple of slides on topology optimization and generative design. That will be in Solid Edge. And I'll do a single demo in that as well. So convergent modeling. In the beginning or dawn of time, we had three main types of modeling. So that included facet modeling, which essentially is point data or cloud data that is assembled in triangles. And these triangles that are two-dimensional then are arranged in a fashion to form a solid or to form some solid feature. We also have wireframe and surface modeling, unit graphics and others, and constructive solids geometry modeling, Unisolid, amongst others. So today, a lot of your CAD packages or CAD software that you're using is a Parasolid. So that combines your wireframe and surface modeling and your constructive solid modeling. So your NXs, your Solid Edge, amongst others, are Parasolids. However, facet modeling today is mostly used for reverse engineering and scan data, as well as visualization, meaning in the gaming industry or graphic design and whatnot. The coding behind facet modeling is very simple, but which is why a lot of programmers, when creating these CAD tools, like to use it. But moving forward, when the models got more complex, we kind of shifted away from it and moved towards a BREP or Parasolid modeling. So what are some sources of point or facet data? So this includes, I mean, you can see on your left right here, this figurine is probably for like a video game, which is made out of wax, or you have your clay modeling, so design with physical models, usually wood or clay or wax. Sometimes this can be easier than CAD systems if you have the right personnel to do them. Data from existing designs. This includes design theft. You have this nice Mercedes here, and then you have this car that's very similar to the Mercedes. Competitor comparisons, duplication, repairs, old designs, so legacy parts that you can scan into your CAD environment to save or modify, and finite element data. And lastly, which I kind of delve into as my case study, is the biomedical industry and how convergent modeling and reverse engineering is applicable to that. This is human body applications, so data from body scanners, custom fit designs, and replacement parts. So today we have convergent modeling. As of 2016, we have the ability to mix this facet modeling with your solid and surface data in a single model. So I'll be stressing this later on in the presentation as well and showing it to you, how you can bring in scanned in data, and based off of that data with a seamless conversion, you can start modeling and as you would any other part to contour or cater to that scanned in data. So the direction that we're moving towards a single system that works seamlessly with features and facet geometry, no conversion of data, and it saves a lot of time. So Siemens is investing in the future modeling. So this includes continuous investments in current and future modeling technologies, and NX is all-encompassing. So this includes NX CAE, topology optimization within NX, and again, convergent modeling, synchronous technology, all within NX. So single application environment for product to production design using any form of geometry. So again, this is traditional wireframe and surface modeling to subdivision modeling and out of convergent modeling. So just to reiterate, any design mediums, so convergent modeling technology, revolutionizing product development. With this next generation of modeling, you have the ability to do design with any design medium, point clouds, meshes. There's a streamlined history. So once you bring in your scanned data, make it into a convergent body, you actually see it in your part navigator, and you can then manipulate it, and you'll see that in your history. Simulation-driven design and optimization, and then really interesting and cool feature is this 3D printing and production of parts and tooling with additive manufacturing. When you do the topology optimization and you essentially have a model that you've created with traditional modeling techniques, you apply certain constraints and loads, then you create a optimized part that is reduced in weight, but it maintains its structural integrity. And then you start thinking about how to create this part. So that'll be done by, or one tool is additive manufacturing. There's tools within NX to cater to that as well. So the convergent modeling technology, this is a really good kind of diagram showing you the process. So you have scanned in data, polygon modeling, you have topology optimization in work pieces, and then you delve into convergent modeling or design without any conversion. This is very, like I said, it's 10 times faster than traditional methods. Once you have your convergent model, then you can start thinking about how to produce it or documentation. So additive and subtractive manufacturing, finite element analysis, tooling, and lastly, documentation. So an overview of convergent modeling technology, some of the capabilities, just to reiterate it. NX design can work with meshes, facets as any other geometry. You have the capability to use scan and mesh data without any conversion. It is history based. So any associative wireframe and feature operations, like if you use a Boolean function to subtract and unite, which I'll be showing later on, mirror, scale, or doing any analysis or assemblies, you'll see in your history. And the business value. No expert knowledge is really required. Reverse engineering, once you convert it into a convergent model, there's very minimal work to be done in terms of cleaning up your geometry and to accelerate concept to production workflows. So what is a convergent body? So a convergent body is a body of mesh types. That can be a closed body or an open body. Your closed body is called the convergent solid body, and your open body is called the convergent sheet body. It's comprised of convergent mesh faces and edges. These two parts here, I'll be working with in a demo actually, so you'll see it firsthand. Body, faces, and edges have full properties and attributes. So your convergent model has a mass, a volume, an area, and a length. And you can also change its view. So you can change its color and object properties. And like I said, your convergent body lives in your part history and partakes in full history-based modeling. So to delve into the biomedical aspect, so how it's important. So there's a lot of trends in the medical device industry that can use this type of technology and skill. That's increased personalization, clinical testing, regulation, and validation. So with increased personalization, it's the use of scanned data. You have a patient and you want to create an implant, which I'll be showing you. You can scan in that data from an MRI or any point cloud data into your system, then bring in an STL into NX. Once you have that, you can model around it. So you can actually create specific parts to cater to that patient or that individual. With clinical testing, you're able to do virtual testing within this interface. And regulation and validation, it's all in a single system. So my first demo here. This is a scanned-in skull from a patient. So what we're going to do in this demonstration is create a cranial implant. So we're actually going to model a part based on this scanned-in data, which will come in as an STL file. So let's delve right into it in our NX space. So I started off as an empty NX document or part, called it cranial implant start. So the first thing I want to do here to go through it step by step is to bring in the STL file. So I go to import STL. Once I do that, there's a dialog box that appears. I select where my file is. It's pretty simple, my skull.stl. And this facet body output type is something that you should know. So you have different options here. You have your Convergent, NX, and JT. Convergent output type basically brings in your STL or scanned data into NX, and you can readily manipulate it. However, which I'll show you in the next demo with the NX output type, you're able to bring in your data and kind of see where some of the abnormalities or deficiencies are with your scanned data. So that enables you to go to the reverse engineering tab and clean up your model. In this case, we're going to bring it in as a conversion model to then manipulate off the bat, and my STL file units will keep it in inches. So once I bring it in, and here is my skull that I can kind of work off of. So the first thing I want to do here, as I alluded to, is manipulating the view of the properties of this. So I'm going to go to the View tab, go to my Edit Object Display, and I'm going to select my object, which is my skull, confirm that, and I want to make it translucent because I'm going to be adding an implant in this area right here. So let's go to translucencies, make it around 84, sounds about right, and confirm that. So once that's done, I'm going to start sketching. Just like you would with any other part, I can go to my direct sketch and I'm going to make a spline, studio spline, select my plane based off my pre-existing coordinate system right here. So I'm going to choose this plane right here. My degrees are, I'm going to select 3 to start. I'm going to select, kind of gauge what area of the skull I want this implant to be. So let's create our first point here, second point, third point, and let's add another point right here, and then we can shape it the way we kind of want it. So that seems about good, and we'll confirm that. So we just created our basic shape, just like you would modeling any other part. Once that's done, I'm going to end up finishing this sketch. So next thing I want to do is I'm going to use some of the features in the Home tab, and I'm going to do a divide face. So I'm going to use that sketch that I just made and make an imprint or divide my actual STL convergent model. So I'm going to select my face, select my object right here, and I want to make it normal to my face and click OK to confirm that. So if you can see, if I highlight it, you can see this area that it kind of split. So now I'm going to use that split area or that divided face to then extrude out and to create my part or my implant, cranial implant. So I want to go to my extrude function, select that face, flip it around. My Boolean is going to be none. I want to be standalone. I'll make this 20 millimeters. And click OK to accept that. Alrighty. So you can see off the bat, I was already able to make a part. It contours beautifully to the skull right here. So next thing I want to do is I want to manipulate this part that I just made, as you would. So you can see my history. I have a convergent body, which is my skull, and I have my sketches and my extrude, right? So next thing I can do, I can actually offset or make this extrusion larger. I'm going to offset face right here, select my face, and it looks like it's in 2 parts. I don't know why this happens sometimes, but okay, well, you can select that face right here. It'll grab that face as well, that segment. Okay, and then I'm going to offset this 5 millimeters. So you saw it grow in size. Let's see if we can do 10 millimeters as well. All right. Okay, so additionally, with the cranial implant, we want to allow for drainage. So you're putting this on the human skull. We want to add some through holes in this implant. So what we can do is we can actually go into the sketch and manipulate it further. What I want to do here is I'm going to go to my sketch area, select circle, go to my plane, and I'm just going to add a circle right here. And I want to make this around 30 millimeters in diameter. Once I do that, finish my sketch. I'm going to go pattern this sketch. So pattern geometry. I'm going to select my sketch right here. I have different options in my pattern geometry dialog box. So my boundary, I'm going to select my curve so everything stays within this boundary. And that seems about right in what I want. So I'm going to confirm that. Oh, my layout is triangle. You can also select square. You can see how that's the layout that you see. It's forms based on the setting. I'm going to keep it at triangle and click OK to confirm. Next thing I want to do is, again, manipulate this model part, this extrusion. So I'm going to go over to my extrude, select my pattern and my sketch. My Boolean is going to be subtract. So I want to subtract it out of my extrusion. And then I'm just going to extend it all the way out. And click OK to apply. So just like that, you can see I have my drainage holes for my cranial implant. And that concludes this demo. You can see that I was able to bring in an STL file, make it into a convergent model. And then from that model, you can then easily manipulate it using your standard CAD tools in your toolbox here, in your home tab. Let's go ahead back to the PowerPoint. Alrighty. So next, we'll kind of get into some reverse engineering. So trends that drive the need for reverse engineering. So this includes 3D printing, competitive analysis, and legacy parts. So with 3D printing, there's different forms of 3D printing, which include SLS printing or FDM printing. With FDM printing in particular, you have to keep in mind some of the support structures in your design. With reverse engineering, you have the ability to kind of manipulate your models to cater it to what your manufacturing style or technique or method is going to be. Competitive analysis, you need CAD data for analysis. Legacy parts, so let's say you have parts that are not in your interface, or you have it on your computer or anything, you can actually scan in that data, bring it into NX, and utilize that model just like you did with that, just like you saw with that skull I did. So importing, preparing, scan data, you kind of see these steps here. So you can scan in data, a file import mesh points. Once you import it, you can kind of evaluate its smoothness or curvature or draft. You can make surfaces off of that. You can evaluate it, like I said, active mockup, so assembly, visualization, section, interface, measure. And then if you do see deficiencies or areas that you want to improve, you can repair it. And I'll be showing some of these tools with the next demo. So snip, fill hole, subdivide, and smooth. Scan data is rarely perfect. So there are issues that come about with your scan data, but that's why we have this wonderful tool like NX to kind of debug and fix those issues. So that includes some alignment issues, surface quality issues, and manufacturing issues. So building on and using scan data. As I said, geometry creation and modification. Once you bring in your scan data, you have the ability to free-form model. You can do synchronous modeling and NX rapid surfacing based on that Facet data. Also, to manipulate the Facet data off the bat, you can just you can decimate Facet bodies. You can do snipping and filling holes, which I'll be showing you, and subdivide the Facet body as well. So here's the next demo. This demo is in two parts essentially. The first part is reverse engineering. The second part is similar to the cranium or the skull, which is more convergent modeling. So I'll be showing you how you can bring in scan data, clean it up with reverse engineering, and then once convert it to a convergent body. Once we have that, then you can start manipulating it as you would. So let's go to our next design space, our next demo. And we call it, I call it the knee blank. So again, this is just a blank NX part. I'm going to be bringing in an STL file as I did with the cranial implant. So I'm going to import STL, select my knee, and you can see right here the Facet body output type. I'm going to make it NX, not a convergent model. So and you'll see the output and why it makes sense to bring it in as an NX. Click OK to confirm that. So I brought it in as an NX facet body, and you can see all these little black lines and marks. So these are essentially abnormalities or deficiencies in your scanned in data. These are points that you want to clean up and fix before you end up converting it to a convergent body. So I'll be showing you some of those techniques. It's included in the, or maintained in the reverse engineering tab. So you have a lot of different options here. You can do rapid surfacing based on your facet model, fit curve, fit surface, snipping, filling holes. You have a lot of different features and merge, disjoint, etc. For this demo, I'll be keeping it short. Again, as Monique stated early on, if you have any other requests later, please get in touch with me or with someone from Saratech, and we'd be happy to help you. Some of the tools I'll be using here mainly are smooth, snip, and fill hole, and then I'll be converting it later to a convergent body. So the first thing I want to do here is the smooth. Dialog box appears. You select your facet body. This is the facet body. You select your draw boundary. So I'm going to go and smooth out this area right here. So you can just simply hold and drag. Click OK to confirm. You can see that it already detects what those deficiencies were and it smooths it out to follow the contour of your model. So then next, just observing this part, you can see in this area it's kind of protruding out. So this is not supposed to look that way. A particular knee probably wouldn't have this. So we're going to actually snip that out and fill it in. So the way we do that is we're using the snip tool, facet body operations. Our snip region is our facet body. Our draw boundary, we go ahead and select this boundary right here, close it out, and then specify our region point, which is on the body. Click OK to confirm that. So you can see it snips it out. Once it's snipped out, we can go ahead and fill this hole. There's different options here as well. So I can go ahead and select my facet body. I select my hole. So NX is smart enough to detect that this curve right here is now considered a hole. So select that curve. And my smoothness. So you have a linear, refined, tangent-based, and curvature-based. I'm going to be selecting tangent-based. Essentially, it's going to follow the contour of this curve and kind of smooth it out. And you'll see what the results are. So click OK here. And you can see how it kind of follows the shape as you would hope for your knee. The next part I'm going to do is, because we don't want this whole area of the knee, essentially the part we're working on will just be in this area, we're going to cut this portion out. So again, we're going to go to snip, select our body, and then select our draw boundary. We're going to snip this whole area out right here, close it out, select our region, OK to confirm, and you'll see that it is hollow. So as I stated before, facet point data is literally points that are formed in triangles, and then these triangles kind of are arranged in a fashion to then create this solid looking feature. However, it is not particularly a solid. So what we're going to do here is fill this hole and then convert it to a convergent model, which then it will act somewhat as more of a solid, which then you can manipulate. So we can go ahead and fill this hole, select the facet body, select the hole, the curve, keep it tangent based, and click OK to confirm. It's crunching it out, and you'll see that the shape, it'll follow a tangent, and it'll create the shape as you see here. Alrighty, so this looks good for what I want to do to create my implant or modification. So I'm going to convert this to a convergent body. So just simply go to convert facet body, select my body. My facet body type is going to be convergent. I want to do automatic cleanup, and I want to delete my input body. And OK to confirm that. It's going to go gray, and then you'll see in the history how it is now a convergent body. All right, so I'm going to go ahead and flip over to the next portion, which is, again, it's kind of convergent modeling to show you again what the capabilities are with that. Let's go into our next part. Is my knee cutting block assembly. You can see that the knee is here, is just the color just changed to red, which you can do with the view edit object display. Let me show you what we're working with here. So we have our knee. We have our knee cutting block part. And let's just make this a displayed part. You can see that this part right here was modeled with standard modeling techniques. You have your extrudes, sketches, planes, etc. And our knee is our convergent model, as you saw, our convergent body. All right. So let's head back to our assembly. This is an assembly, so you can move. This was just placed right on top of the knee. So I can go ahead and move this once it loads, right? But we're going to keep it at that point. All right. So the first thing we're going to do here is go to our assemblies tab, and we're going to do a wave geometry linker. So what we want to do is we want to link these two bodies together. What that means is when you make a modification to one body, it will know what the interfaces are between these two bodies. So when you make a modification to one body, which you'll see shortly, it will act on the other body as well, to say it in the simplest terms. So I'm going to go ahead and do associative. This means that you'll see it in your assembly or part navigator. My type is a body. I want to hide the original for this one. So just select it and apply. The next one that it will be linked to, it'll recognize what the interfaces are, is my knee body. I want to not hide the original and apply. So I'll show you what the associative means once it loads. Okay. We'll go to our part. So now you see it's associative, so it's in your part navigator, and you see these two linked bodies. So you can go ahead and hide it. So that was your first link body and your second link body. Let me hide these two. There we go. All right. So next thing I want to do is I want to offset this knee, just as you would any other body. And remember, this was a scanned in data. It's a scanned in knee. So I can go in to my features tab and do an offset face. I'm going to select the face of my knee. I'm going to offset it 1.5 millimeters. Shortly after it recognizes what my surface is in a second. All right, 1.5. Once I do that, you'll see how it kind of blends into my part here. Furthermore, it was already blending in regardless. Maybe I didn't stress that enough. So as you saw how the part overlapped in the knee, essentially what we're going to do is we want to modify this part that we designed to fit the knee perfectly, right? So you saw before how it kind of laid inside the knee. We don't want that. So that's the reason why we're doing this convergent modeling, right? Is to reshape this part to contour to our patient's knee. So after we did the offset base, we can use standard Boolean functions. It was one of the slides I mentioned how all the Boolean functions and all that on your convergent models will show up in your tree. So we can go over to subtract, select our body, which is our tool that we did standard modeling techniques on, select our knee, and then click OK to confirm that. So now you can see right here how we kind of cut out that shape that we wanted and how this will fit on top of our knee. Next, we want to go back to our offset face to show you what this wavelink properties did. So we go to offset face here. You can see the knee appears. You can go to edit parameters, and you can see that although I never selected this face to offset, I actually selected the knee body or face to offset. You can see that it already detects this because this is a shared interface between the knee and the this part. So I'm going to change this to 1. When I do that, you'll see how this part gets thicker. Alrighty, and after that, I'm going to go ahead and show you the result. So here's our original knee. You can see how it fits very nicely on top of our knee, and you can see there's a nice gap here. There we have it. So we were able to bring in an STL file. We had a part that was traditionally modeled. We're able to modify this part based on our scanned in STL data to then fit perfectly to our patient's anatomy. So let's head back to the PowerPoint. We're wrapping up here. So last section, a couple of slides on this is topology optimization and generative design. The demo on this will be in Solid Edge actually. So impact of additive design to production processes. So you can see this part here. It's a very organic shape. This was for sure done in topology optimization. It was optimized and topology optimization was done on it. Essentially, what that enables you to do is you have a part or your workspace that you modeled, and then you can apply different loads and constraints to this part to not compromise strength and to minimize weight. It's a very powerful tool, and it works beautifully with 3D printing, because once you have that optimized shape, you can just feed it right into your 3D printer, especially if you have a powder printer, like an SLS printer, when you don't have to really think about support structures, and then you can crank out a prototype or a model. So with the impact of additive design and production processes, you have your end-to-end support to design, optimize, and produce parts using additive manufacturing processes. Siemens in particular is leading in the development of next generation software and processes to enable this shift. So you have the ability to do requirements-driven design and validation, lightweight structure design optimization, design rules and validation, performance optimization and validation, and lastly, build processing and validation. So design for additive manufacturing. Again, I'm kind of tying these two things together, the topology optimization, generative design with additive manufacturing. All operations are in NXCAD or Solid Edge ST10. There is a capability within NXCAD, but I'll be showing it today in Solid Edge. You have the ability to create multiple load cases, and optimized model can be refined with Convergent Modeling. We have a single demo here. It's funny because this is a part that I made, which I hope to 3D print later on. It's actually a water bottle cup holder adapter for my car. I have a rather large water bottle, and it doesn't really fit in my car's cup holder. So I thought this would be a great design to use to optimize, because I want a really cool organic fluid design to both support my water bottle, but also look nice. So we'll be playing around with this one really briefly. Let's head to our Solid Edge. So here's my wonderful cup holder that I designed. It's a pretty simple model. It fits in my car's cup holder, and it's supposed to hold my water bottle right here, right? So I want to do a generative study on this part that I made. So it's in the generative design tab. This tab is very easy to use, which is really awesome. So things you have to do is select your materials. Like I said, I want to 3D print this. So I'm going to make this in nylon, general purpose nylon. This is important because depending on your material, that has an effect on what kind of stresses you'll see once you generate, or you have the option to show your stresses. You can once you create your material, you can create your generative study. So I just named this generative study 1. Select your design space. What actual space are you working with to do your study? It's the whole thing in this example. Then you go on to select your regions that you want to preserve. So once you select that option, I'm able to go in here, preserved, and create an offset of 0.1. Next, I want to preserve the area where my water bottle sits. So I'll select that face, make that 0.1. And then next, I want to preserve these structure that kind of holds the water bottle in place. So we'll preserve these two and make that 0.1. Alrighty, next we can apply your forces. So what kind of loads will this see? And based on those loads, it will optimize your shape. So the forces, I'm going to apply it to the face right here. And let's just make it 10 pounds of force. You also have the ability to do a pressure, so a force over a particular area, or a torque. Lastly, your constraints. So how will this be fixed? So this will be sitting in my cup holder. I'll just do a really simple constraint for this particular example, so I'll just fix it on the bottom here. My offset, do 0.1, and confirm that. Once that's all done, it's a very simple tool to use, and it's a very streamlined process. You go to your generate, and a dialog box will appear for you to select more options. So your study quality, so how precise do you want your results to be? Your target mass, so you want to reduce your mass by 50%, 30%, etc. Here's my original mass, it's pretty light. Based on my nylon properties, it's pretty light. And then your allowable stresses, you can set these all in. For mine, I mean, this is a consumer product, so this isn't really that critical, but if you're doing a part for automotive, this will be much more critical. Then you click generate. Once you click generate, it'll take some time to actually crank this out, even though it says 28 seconds. It depends on your system. I have a part already done, which is here, it'll create a constructive or design body. You have the ability to toggle between a construction body and design body, which is right-clicking, and then do toggle design and construction. This right here is the end result. You can see if I hide this, here is my optimized part. So this is what it will spit out after I click that generate button. You can see, it's a very organic shape. My thickness here was maintained. So it's a pretty cool part. So I may end up feeding this in a 3D printer and then spitting this out to then use in my vehicle. Alrighty. So heading back to the PowerPoint, basically wrapping up here. I think that was the final slide, actually. Yeah. So just to summarize in words, you're able to see convergent modeling, reverse engineering, and topology optimization. With convergent modeling, we kind of delved into biomedical space because what you have the ability to do is to scan data, bring it into your design space, and then use reverse engineering to clean it up, then make it into a convergent model. Once you do that, then you can use that model to then design your parts. So whether it be an implant for the knee or the skull, etc. Topology optimization enables you to have a part, apply your constraints and loads. And once you do that, it'll spit out a body that is optimized to reduce weight, but also keep a structural integrity. Then you can feed that into a 3D printer and then start prototyping or production, whatever it may be. So that concludes my portion. Again, if you have any specific things you want to see in terms of reverse engineering or convergent modeling or topology optimization, please reach out to me or Saratech in general. I'll be happy to help you.
Hey, Edwin, so we actually got a question in from one of our audience members. Marvin
Sure.
asks, are there settings to allow larger STL files to process, like a scanned boat hole? File is 3G and it is running really slow and trying to reverse engineer.
So he's having issues because it's a pretty hefty part, or it's a hefty model.
Yes.
Can you repeat the question? Oh, okay. I have to probably look into that further and see. Well, working with larger parts to bring in convergent modeling. Yeah, I don't have an answer for you off the bat. Let me go back and research some of the features or toggle the options to see what kind of things we can do to make it smoother to bring in a large STL file. Yeah, that can do with your system that you're using, but also I think working with large models. Well, Mehdi's doing large assemblies in NX for the next session, but there can be an option to toggle. I haven't played around with that too much, but I will get an answer to you through email. So thank you for your question, though.
Awesome. Yeah, I will make sure to give you the information so you can get back to him.
Okay, awesome.
And then also he asked, do you know of any tutorials in reverse engineering in NX? Do you know if there is anything that you could probably help him out with?
Tutorials in reverse engineering in NX. I may have to get in touch with Siemens guys, because I don't have anything on hand. I'm sure there's a huge database with, that Siemens has. But I can for sure investigate and get back to them really quick on that.
Perfect. Awesome. Okay. Well, thank you. Great presentation. And to all our audience members, our next session is how to work with large assemblies in NX. Will be presented by Mehdi Razawan on November 16th from 11 to 11:30. And thank you everyone so much for coming in. If you're interested to take it to the next level, we offer hands-on training, classes for software users of all levels, engineering services to address your demand for advanced engineering capabilities as well. And we will be posting this video to YouTube later today. Feel free to pass along to your friends and colleagues, and be sure to subscribe to our channel, follow us on Twitter and LinkedIn for upcoming webinar dates and topics. And if you could, please just stick around for about 10 to 15 seconds afterward to fill out the survey. Let us know how we did and what you liked. And thank you again so much, everyone, for attending, and have a great rest of your day.
Thank you.